So far, we've talked a little bit about what units are and how to convert them from one form to another. We haven't talked about why they're useful, and in fact they're very useful, very powerful. So one way that you can do it in a very pragmatic fashion is units are useful because if you go through a problem, and I highly recommend this, if you go through a problem and as you're manipulating your variables and you're manipulating your numbers and your values and your properties, always keep the units attached to the number that they belong with. So if I have a mass that is 3 kilograms, never write just 3. Always write 3 kilograms. Because then, if you get to the end of the problem and you're looking for a velocity, but you have units of mass, you know your answer is incorrect, and you're able to go back and try to figure out where you went wrong. So units are a great check as to whether or not you are doing the problem correctly. Another useful purpose of units is the ability to look at an expression that you may not have seen before and very quickly figure out what it's saying. So suppose I wrote down mv squared over r. This probably means nothing to you. But what I'm going to tell you that the m is a mass, the v is a velocity, and the r is a radius, which has units of length. So let's go ahead and this symbol, square brackets, so if I do m in a square set of square brackets, it's evaluating this for its units. So the units of the mass are mass, which in this case we'll say are kilograms. The units of v are velocity, which I'm going to say is meters per second. And the units of r has units of length, which is meters. So let's use the units and plug the units into this equation. So we're going to have kilograms times meters squared over seconds squared divided by meters. We can bring the second squared down to the bottom. So I'm going to have kilograms times meters squared divided by meters times seconds squared. Now, meters squared divided by meters is just the meters on top. So I'll get rid of the square, get rid of the meters on the bottom, and I get kilograms times meters divided by seconds squared. You might not recognize this, or you may. This is equal to a newton, which is the unit of force. So now, you can look at this and say, oh, I might not know exactly what's going on here, but this is a force. And indeed it is. It's the force felt by an object that is experiencing centripetal motion. So if it's spinning in a circle, an object, let's say, is on a strain, is spinning in a circle, m is the mass of the object, r is the distance between the mass and the point it's connected to, and v is the tangential velocity of the object. So you can reason that this is a force and look at the variable and try to figure out more, but just knowing it's a force is valuable in and of itself. But this isn't all that units do. In fact, units can also be used to determine whether or not an equation makes sense. Suppose I want to look at the equation for kinetic energy, which all that is the energy of an object that's moving. So as I throw this up, it has kinetic energy. So kinetic energy, I'll write as K, and the equation for it is 1/2 mv squared. 1/2 is a dimensionless factor. It has no units, it's just a number that's kind of stuck there. But we can look and see what the units of these two things are together and whether or not they have the units of energy as they should. So the units of mass are kilograms and the units of velocity are meters per second. So plugging this into here and ignoring the dimensionless factor, we're going to have kilograms times meters squared over seconds squared. You might say this looks very similar to the newton, the unit of force, and indeed it is very similar, but not quite. This is actually equal to joule, which is the unit of energy. And kinetic energy does indeed have units of joules, so this equation makes sense. But the coolest function of units is that they can actually be used to predict what the formula is for some value. Suppose I want to know the energy of an object that is held some distance above the ground. We know it has some energy because if I let go of it, it's moving and it has kinetic energy. And we'll get to this, but kinetic energy can't be created or destroyed, conservation of energy. So there's some energy associated with an object as I hold it high up above the ground. So the two properties about this object that I know are I know its mass, and I know that it has units of kilograms, and I also know how high I'm holding it above the ground. I can measure that. So let's call that height, which I'll write as h, and that has units of meters. So the last thing that we're going to need is when I drop this, there's an attraction to the Earth. That's known as gravity. And there's a constant which is associated with that, which I'm going to call, or is called, g. Now g is an acceleration, and therefore has units of meters per second squared, meters per second, which you'll notice is close to velocity, but has the extra factor of second in the bottom. So I want to find an equation for energy based on these three things. So I know energy should have units, I'll write energy as E, has units of kilograms times meters squared over seconds squared. So how can I combine these such that I get the proper units? This one is actually very straightforward. I want a kilograms on top, so I'll say I'll take an m, and I want to multiply it by a meters squared over seconds squared. Well, I have a meters per second squared, and I have an extra meter up here, so I'll just say, okay, m times g times h. So I'll say the potential energy, which I'll call U, is proportional to mgh. The reason I say it's proportional is because you'll remember that kinetic energy, when we talked about that, was 1/2 mv squared, and it had this dimensionless factor up front. The dimensionless factor can't be predicted, but the important part of this equation are the units, are the properties here. The 1/2 is pretty irrelevant. So indeed, we are correct. Potential energy, in this case, is actually exactly equal. Potential energy equals mgh. So just based on what values we knew about an object and what we wanted to find, we were able to predict the equation for a value for that potential energy. So units are incredibly powerful, and you can use them sometimes to just guess what the answer is to a problem. If I give you certain variables, and I say, here's the mass, here's the energy, here's the length, here's this, find how fast it's going to accelerate. You can sometimes just take the things I gave you, look at them, say, oh, these are the units, I can combine them and get the units of what he wants, and that's a perfectly legitimate, valid way of doing the problem, is just predicting what the answer is, guessing what the answer is, to a dimensionless factor, purely with units. And that's why we do units, and I try to stress that they're important, because they're actually valuable problem-solving tools.